Okay, moving on to torsion and shear, mostly shear. Torsion follows similar principles. There's a link here to a video that's worth checking out. Maybe I'll pull it up to a special spot or a good spot. Okay, so you can see here this tension-filled action developing. That's kind of the key of what I want you to get from these videos. Okay, so moving on. The motion of shear, we typically think of shear like scissors tearing something apart. When we apply that to beams, we're thinking about sliding relative hunks of the beam relative to each other. Shear stress in a solid cross section tends to be the maximum at the middle and less at the end. And in a wide flange section, it's very little in the flanges for two reasons. One, there's a lot of area, and two, it's not as stiff to carry the shear force. Okay, so here's a reason why shear matters. If we take all these papers and don't glue them together and try to make a beam out of it, we basically have no beam. Whereas if we glue them all together, they can hold quite a bit of load. Okay, one of the key things to understand about shear is if we have shear stress on a little part of our beam, if we rotate that, or 45 degrees would be 90 degrees on Morse circle, but 45 here in reality, we end up with a tension and a compression. So that's what creates this tension-filled action in a pure shear test. So in one direction we're shear, in 45 degrees to that we're tension and compression. Okay, so kind of this relates to that, like we were talking about. So in a girder, and you see these in highway girders a lot of times, you'll have a vertical stiffener, usually less in spacing than the depth of the girder. And it essentially creates a truss where tension can come through the buckled portion of the web, compression through the stiffener, and then back through tension through the buckled portion. All right, we're going to use the direct shear method mostly because most of what we design fits in those parameters. So the basic equation is 0.6 times yield times the area times its coefficient. The coefficient relates to a buckling propensity, and that's given here in this term. So we'll calculate H over TW, thickness of the web. If it's less than this expression, then our CV is 1, which actually is the case for a lot of sections in the manual. All right, sometimes people ask, why is there a 0.6 on the yield strength? Turns out that tension yield is the yield strength we're specifying, and shear yield happens about 60% of that value. So generally, on any shear equation, you'll see a 0.58, 0.6, maybe 0.55 on the yield. Okay, so more on those equations, and those are things you can get into, and the example covers this more thoroughly. The shear centers, so we want to think about where we're loading a member and how that may or may not affect things. On a wide flange, we load in the center. On a channel, ideally, we want to load at a certain eccentricity away from the channel to prevent torsion. It's not always realistic to do it that way. And then briefly, there's a few slides on torsional strength. Generally, we want closed shapes. For torsion, they're far more efficient in torsion than an open shape like these top three right here. All right, briefly on drawings. This is a detail of an existing column. We added angles to it to give it a greater both compressive and flexural strength. And the key to this was sizing, well, one of the keys was sizing the bolts to make that connection. And we ended up bolting this because it was being installed in an area that welding wasn't going to be permitted. All right, some simple shear connection examples. So this is a double clip. So the beam, at the end of the beam, it produces whatever reaction it has that runs through the bolts, through the clip, through the other leg of the clip, through the bolts, and then into the web of the receiving beam. So this is pretty common type connections. We use double clips in industrial settings and these single shear tabs in more commercial settings. I think that wraps this up. So similar to other modes, there's an example here that does the same beam in the last example, and then also does a built-up girder and a torsional member. All right, I will talk to you in class.